William, are you starting the recording?
No, I'm starting just
Okay,
YouTube.
I'll start the recording. Everybody can see the slide?
Yes.
Okay. Ooh, interesting question. You don't have a gray blob over it, do you?
You're live.
That's fine. Okay.
Shall we let them in?
Go for it.
All
Or
right.
I'll hit the button.
Please do. Let's admit all.
I've also started the recording.
Welcome, everyone. Good morning, good afternoon, or evening. My name is Deborah Paul, and I'm currently serving as Deputy Chair of the Biodiversity Information Standards TDWG organization, and I'm joining you from Tallahassee, Florida. If you're just joining us today for the first time, welcome. And if you've been with us all week so far, we trust you are enjoying the non-overlapping sessions and the social hours as much as we are. Hint, there's one social hour left. Note we're using Zoom meeting software today, and this allows participants to use their microphones and cameras when appropriate. I would like to remind you that in registering, all of you agreed to abide by a code of conduct, and failure to respect it could lead to removal from the session, and you would not be able to rejoin. Again, we would like to gratefully acknowledge the financial or in-kind support for TDWG 2020 from the following organizations: Pensoft Publishing, the JRS Biodiversity Foundation, the Global Biodiversity Information Facility, IDIC Bio, the Distributed System of Scientific Collections, DISCO, and the Atlas of Living Australia. Without them, this seemingly free event, with over 770 registrations so far, would not have been possible. Please note, our annual TDWG business meeting follows today's plenary speaker. You don't need to be a member of TDWG to attend. All are welcome to come and learn a little bit more about the inner workings of TDWG, about what happened last year and what might be coming up next, and how you could participate. That said, there's an exciting reason why we're all here right now. We either get to wrap up or start today's sessions with a plenary keynote by Kenichi Ueda, software developer and co-director of iNaturalist. On behalf of the Executive and Program Committee of the Biodiversity Information Standards, or what we affectionately call TDWG, welcome, Kenichi. Being a biodiversity standards organization, our members are dedicated to liberating all sorts of biodiversity data and increasing access to it. And while we're all aware of the knowledge discovery potential that these data hold, it makes sense that we're all very interested in images, novel uses, and reuse of them. We're thrilled to have you with us today so that we can learn a bit more about the magic of INAT's tools and what we can dream about in the future. I will moderate this keynote along with some help from my colleagues Holly Little and James Macklin and Ellie Wallace. Please feel free to put questions or comments in the Google Doc we have prepared. Look in the chat. Once Kenichi has finished his talk, we will have time for your questions. As I mentioned earlier, please be respectful in this virtual environment as outlined by our code of conduct. Let's begin first by welcoming Kenichi by putting an exclamation point in the chat if you use INAT. And one more task for you. If this is your first ever TDWG meeting, please put a +1. Thank you. Now it is my pleasure to say, take it away, Kenichi, for your talk entitled An Overview of the Computer Vision in iNaturalist.
Awesome. Thanks, Deb, and thanks for that great introduction. And thank you to everyone at TDWG for having me here. It's really great to be able to talk to you folks. So let me try and share my screen and not share some other embarrassing screen. Presentation and playing. All right, is that working for everybody? Cool, awesome. Thanks, James. You're one of the only thumbs up that I can see in my display right now. All right, so I got some interesting UI going on here. Okay. Well, thanks for the introduction. Yeah, I'm Kenichi. I'm one of the co-directors and co-founders of iNaturalist. And yeah, the folks at TDWG asked us to give a presentation about how we use computer vision technologies and systems on iNaturalist. And I just want to preface this by saying I'm probably not the best person to be giving this talk. I do not work directly on Inet's computer vision systems. But I asked around for the folks who do directly work on it, and none of them were feeling up to giving the talk. So instead, you get this overview by me. So apologies in advance if any of this seems overly simplistic. But if anyone does have technical questions or more detailed questions that I can't answer, I'm happy to relay them to the folks on the team that can answer them. And hopefully I can either paste the answers into the Google Doc or post them somewhere else so we can make it work. Okay, so for those of you who do not use Inet, which I guess is a minority of you given all the exclamation marks in the chat, iNaturalist is a platform for basically sharing media evidence of your encounters with non-human organisms, which is a long-winded way of saying that if you are out for a hike and you see a weird flower or a bug or a snake or a worm, you can take a photo of it and post it on the internet, and people all around the world will be able to see it and potentially discuss it with you, maybe add some identifications. And so that's what you're seeing here in the screenshot. It's just an observation on iNaturalist that someone posted, and then a discussion ensued about what kind of organism this might be. You can see that there's a map showing the location, and there's a date, there's the identity of the person who uploaded it, a bunch of comments, and then a bunch of identifications. So we also crowdsource the identification process, and everyone can sort of offer their opinion about what something might be. I use this as an example of an observation because it's not only an example of the kinds of data that go into an observation, but it's also an example of quality of media evidence can influence how we identify things, right? So this is a relatively blurry picture of a snake, and it's not immediately obvious what kind of snake it is. We also have mobile apps on iNaturalist that make it very easy to record this kind of information. All of you probably have a smartphone in your pocket right now, if you're not actually attending this talk on your smartphone. But the apps make it super easy to record photos, obviously. They also record location and dates, which is basically what you need for sort of a photo vouchered specimen and the kind of information and experiences that we want to record on iNaturalist. Our focus on iNaturalist is facilitating those kinds of experiences outside where you are slowing down and paying attention and noticing the organisms around you. But a byproduct of that activity is a lot of interesting data. So every time you have a location and a date and a species name and some evidence to support that claim, that's interesting biodiversity data that you guys are all perfectly aware of. So iNaturalist provides ways to explore that data. So this is an example of a map on the website showing all the lepidopterans in Contra Costa County, which is close to where I live in Oakland, California. Over there, do I have a pointer? Maybe I don't. So this is one way of exploring data on iNaturalist. We also have sort of taxonomic views on the data. You can see the most commonly observed taxa in a given area or within a given set of observation search parameters. And this is something that we all commonly do on iNaturalist, but it also plays into how computer vision works. And I'm going to get to that in a little bit. Most importantly, though, iNaturalist is a community of people. So we at iNaturalist are technologists. We write software, we design things, but none of it works without people submitting observations, identifying them, talking to each other. It really is more this slide than the previous slides. The technology is really just a conduit to connect all these different people. And that's really our mission at iNaturalist, is to connect people to nature through technology. I like to emphasize this at every talk I give, that the technology is just a means to an end. We're not even in this primarily to make data. We are in this to help people feel more connected to the natural world, to slow down, like I said, and pay attention, and start to think of other organisms as neighbors and as peers, as other creatures that we share this planet with. So that's what we're trying to do at iNaturalist, and everything else is kind of not a sideshow, but a byproduct. Anyway, how does computer vision factor into all this? So every time you make an observation on iNaturalist, and you've got your photo and the location and the date have all been filled in, the next thing you probably want to do is either figure out what it was you saw, or if you know what it was you saw, add that name. So every time that you tap that field that says, what did you see, you get an interface like this. So this is from the Android app. And right when you tap that piece of that question, this interface starts to suggest species that you might have observed. And so what's happening here is that the photo is being submitted to Inet, and we're analyzing it, and we are using a computer vision system to suggest what species might be present in that photo. So this is an example of a plant growing in my backyard. And if I didn't know what it was, I could take a picture like this, and it would suggest and say, this looks like it's probably in the genus Ceanothus, and here are some suggestions of what kind of Ceanothus it might be. And so that's kind of the primary experience. And this solves an important problem in natural history generally, and that's just ignorance. Many people don't know anything about nature. They sort of lack the basic vocabulary to even describe what it is they're seeing. So to someone who just doesn't know the name of any plant and couldn't tell a Ceanothus from a phormium from an oak tree, this is enormously useful. This is a toehold in that wall that allows you to start to apply names to things. So if you don't even you don't not only do not know your plants, but you don't know what kind of field guide you might use, or you don't know anyone who knows their plants, and you just have no access into this world of natural history, this provides an immediate channel to start getting some recommendations about what it is you're seeing. So that was really the primary problem that we were trying to solve with computer vision technology, is just to provide that immediate response. So iNaturalist does provide that itself through people. When you submit an observation, hopefully you get an identification eventually, but that's not guaranteed. And it can take, between minutes and days to months to get that kind of feedback. A computer vision system provides that feedback instantaneously, relatively instantaneously. So that's enormously useful for people who are just getting started in natural history. I should also point out that it's enormously useful to almost anyone in natural history, because we all are ignorant of something. I'm very knowledgeable about the natural history of the San Francisco Bay Area, but if I go to Costa Rica or Russia or Australia, I don't know anything. So even though I'm fairly experienced in one area, this kind of technology can really help me, an experienced naturalist, learn about things that I'm less experienced about. So that problem of ignorance is one problem that we were trying to solve with computer vision. Another kind of unexpected problem it solves is the problem of the tedium of typing in species names. If you use iNaturalist, you might know that you're just constantly typing in species names, or constantly applying species to photos. And computer vision can act as a kind of autocomplete technology. So every time you go to add a species name, we automatically show these suggested results based on the photo that you're trying to identify. And even if you know exactly what you were about to type, and you know exactly what you want to identify it as, if the right result shows up in the top, that saves you a few seconds of typing, and you can just choose the thing that you wanted to do. I do this all the time. I'm constantly identifying common things that I know perfectly well, but I don't feel like typing out the letters C, L, R, K, I, A, and it was just much easier to click a result. So that's a second problem that computer vision kind of solves for us. Interestingly, it doesn't make it, but it indicates that, the fact that someone used a computer vision assisted interface for adding identification doesn't actually tell us anything about their level of knowledge. We do indicate that on the website. We show in a marker that says like, this was added with a computer vision interface, which I actually resisted pretty strongly initially because I know, and hopefully you know now too, that it doesn't really mean anything. It just means that someone used a particular tool. It doesn't mean that they were ignorant or if they blindly chose something, they're just obeying a machine. All it means is that they used a particular piece of software. So that also makes it interesting to kind of, for us to analyze and assess, you know, like, is computer vision technology misleading people? It's really hard to tell because we don't know what kind of expertise they have. Another way that people interact with computer vision systems on iNaturalist is through Seek. So Seek is a separate app that we built. And while iNaturalist is relatively open-ended and more of a tool to assist you, Seek is more of a guided experience in the form of a game. So Seek provides a Pokemon-like game experience where the app recommends taxa for you to go look for based on nearby iNaturalist observations. And then if you find them, well, you'd go and find them, you take a picture, and the app determines whether or not you found the thing you were looking for or whether you found something else. And that's where the computer vision is coming in. We have a computer vision model in the app on your phone that is trying to recognize what it is that you've got your phone pointed at. If you haven't tried it, it's super cool. It gives you sort of real-time results of what you're looking at. You can move the camera around and you have to sort of reorient the camera until it gets a picture that's it can identify the species. And that's what this UI is showing. So this is a very different UI from the previous UI that I just showed you. Sorry if I'm using too much jargon, but UI is user interface, different kind of look to the software and the different way of interacting with it. Seek is much more oriented towards giving you a single answer or getting you towards a single answer. And it is also able to get finer or coarser taxonomic judgments about what you're looking at. So if you might start out from one angle and it often says, it's a dicot, try and get closer and get a better picture so we can get some more resolution and identify it a bit finer. And the more you get an image that it can identify better, the closer or the more further down the taxonomic tree it will go. And it indicates that through these dots. So you're trying to sort of fill the dots to get a species level photograph, and then you take the photograph and then you've collected the species and maybe you earn a badge. So that's how the system works in Seek. So what's actually happening when the computer vision system is giving you some suggestions? So this is a very crude schematic that I put together to indicate kind of what the cycle looks like. So I'll try and walk you through it, and I'll probably dwell on this slide a bit longer than I probably should, but such is life. So basically, anytime you're getting automated suggestions on iNaturalist, you're starting by submitting a photo, hopefully a photo you took, as well as a location and a date. So the first thing that happens is you're throwing this data up to an iNaturalist server. And the first thing that happens is the image is fed through this computer vision model. And that's basically it's a system that takes an image as input.
Tu vois, c'est iNaturalist, Balou. C'est supporté par...
Sorry, was that a question?
No, somebody unmuted themselves. Please keep going.
Oh, okay. Such is life. So this computer vision system is basically just an image in and a list of taxa out. And those taxa come with scores, which our collaborators who know a lot about computer vision tell us are not probabilities. So I don't really know why they're not probabilities, but they are useful for sorting the results, although they don't necessarily mean that the image is like 90% probability being one particular taxon. But we got a list of taxa and a list of scores. So we could turn around at that point and just return that list of taxa to the user and say, like, here's the taxa that we think might be in the image you submitted. But we can actually provide a much better result if we combine those vision results with observational data based on nearby observations. So what we do is we take the vision results and we take the top X taxa. Here, we're just assuming it's 5. And we say, is there a taxon that contains all of those top 5 vision suggestions? And if there is, as in this case, we might say, you know, those are all arachnids. So there's a common ancestor to all those taxon, and it's arachnida. And we might use that to start an observation search. So trivially, we might say, okay, we have these vision results. We know there are it's probably an arachnid. What are the most commonly observed arachnids in the iNaturalist database? If in your original request, you also included a location and a date, we can further condition that observation search and say, okay, let's look for arachnids close to where this person was, specifically within a 3 by 3 degree grid around your location. So in my example here is showing, let's imagine that I'm in Oakland, California, which I am. So we look at this 3 by 3 degree cell around me. If I said that I made this observation in October, we would also perform a search that is in the months surrounding October. So we'd look in September, October, and November for all years. So that helps us narrow down these observation results. And we get, again, a list of taxa, and we actually get a list of observation counts. And we normalize those counts into a 0 to 1 range. So it's roughly matching the scores that we get out of the computer vision model. And that might be quite different, right? So the observational data is not saying much about the visual similarity of the image. And it might actually contain some taxa that the computer vision model does not know about. So we might be injecting taxa based on the observations that are not even in the vision model. So now we have these two lists. We've got this list of vision taxa and we have this list of observational taxa, and then we combine them. So we might use the observational scores to boost or demote some of the scores from the vision results. We might insert some taxa that were not in the vision results, and then we return that to the user. So if you've used Inet, you're probably familiar with this kind of UI where it says, we're pretty sure it's in blah. And in this case, that blah is that common ancestor that I just talked about. So that's a common ancestor that we derived from the vision results. And then you're going to get a list of 10 suggestions. And we say, like, here's 10 suggestions for things it might be. And you'll see these labels that say visually similar or seen nearby. Visually similar means that it was a result that came out of the vision model. So that's basically what that means. It means the image looks like images of this taxon. And then the seen nearby part means that it is a taxon that was observed near where and when you were. So it's in space and time. So those are the results you get back. And that's like the fundamental interaction loop of Inet's automated suggestions. So that all happens, in a second or two. What is that robot doing? That's the part that I don't really understand very well. I basically think of it as a bit of a black box, but like most machine learning systems, it takes a bunch of inputs and has a bunch of outputs. In this case, the inputs are all the pixels in the image that you are submitting, and the outputs are taxa that might be contained within the image. If you care, it's a convolutional neural nets. We use Inception v3 as our network. But for me, at my level of knowledge, it's just easier to kind of black box this and say image goes in, taxa come out. What I do know about machine learning systems is that they are almost never better than the data that they've learned from, much like people. If you are training based on bad information, you are going to get bad knowledge as a result. And machine learning systems are no different. So if iNaturalist automated suggestions are any good, it's really because our images and our training data is quite good. Most things are pretty well identified. And the training data set is uniquely suited to the tasks that we put it, because it's basically the same task. We have lots of images of lots of taxa, and the kinds of images we get, or the kinds of images that we're training on, are the kinds of images that people submit and are feeding through the ultimate system. So our system isn't trained on a bunch of identical specimen images on a white or gray background at very high resolution. And it's not trained on National Geographic level, super artistic, awesome photographs. It's trained on the kind of photograph that you take when it's just started to rain and you're holding a kid in one hand and the kid is crying and you just saw a salamander. That's the first time you've ever seen that salamander, and you're balancing and you just take a really crappy blurry photo. That's what most of iNatural's photos are like. And that's our training data set. So it's uniquely sort of conditioned based on the training data to be good at recognizing taxa in those kinds of photos. And as I mentioned, we have a lot of them. So this chart is showing how many photos were used to train our computer vision models over time. So on the left is the first model we trained, and it had a little over 2.5 million images. And on the far right is the model that we're training right now, which is being trained on about 17.5 million photos. The one that's in production that you're probably using right now is the second to the last on the right, so that 12.5 million one. So there are a lot of photos. There are also a lot of taxa. This graph shows the number of labels or classes, which are basically taxa, that each model knew about or knows about. So the one that's in training now will know about 35,000 taxa. The one that's in production now knows about 25,000 taxa. These two colors are indicating different criteria for how we, whether or not we include taxa in the training process. Initially, we were only including taxa that had a certain number of photographers. So we wanted a minimum number of people who had observed something before we would include the taxa in the model. Eventually, we realized that it was a lot easier to just use a number of observations criterion. So now it's taxa that have over 100 observations, 50 of which are verifiable. It's a little bit easier to compute and export, and it didn't really make much of a difference in terms of accuracy. It did, as you'll note, cut down the number of species that we were including, but that we recovered from that with the next training run, and now the most recent training run is quite a bit higher than both of those. What else did I want to say about this? Oh, I also wanted to point out that when we do select taxa for training and we export photos for training, we do cap it. So we say, you know, we're never training on more than 1,000 photos per taxa. So that growth that I showed here in the number of images is not just, you know, 1 million more people adding 1 million more mallard observations. This is a lot more species, different taxa being observed, and the bulk of them are species. So the model is actually it is legitimately getting better at recognizing more things, or at least it's learning to recognize more things. Whether it's getting better is a bit debatable. This is the spatial distribution of the images that go into the training process. So the first model is in the upper left, and the most recent model that we're training now is in the lower right. Couple of things to note here are that there has been really significant growth in observational activity in Russia, in Africa, in South America, in Australia. And these are in some places due to direct partnerships with groups like the Atlas of Living Australia, and other places there's been more organic growth like it has been in Russia. But our training data for the computer vision systems is pretty biased. That's one thing to note here, very biased towards North America and Europe. Even in North America, it's very biased towards California, which means that, you know, people all over the world, if they see an orange flower, it almost always says like, oh, it might be a California poppy. And, you know, maybe it is, but probably not. And that's an indication of bias in the training data, because we just have tons and tons of, the system knows a lot about taxa in California and not so much about taxa in, you know, Siberia. But that's changing over time as we get more observations in more places. Anything else I wanted to note here? Nope, I think that's pretty much it. So what does it take in terms of people to make a system like this happen? I wanted to highlight both Alex and Grant here. Alex is our iPhone developer, and he really spearheaded our computer vision efforts. I remember early on in the process, he came to Scott and me and was like, you know, we should try this out. And we're like, nah, that'll never work. No one's ever going to be able to build a computer that can like recognize species in photos. That's impossible. And then like Alex did a little prototype, and it was like 95% accurate at identifying lady beetles in California. And we're like, oh, I guess we're there. I guess it does work. So Alex is a software engineer and an artist, and he basically taught himself about computer vision and machine learning. But he doesn't have any specialized training in the area. He just sort of took some Coursera courses and learned as much as he could. And then Grant Van Horn is a researcher in computer vision. So he is an actual expert in this area, and he was super helpful to us in the early stages when he was a grad student at Caltech, basically in advising us and teaching us and kind of acting as our computer vision professor, helping us out in training, especially in like adjusting the model to fit on the phone for Seek. So I just wanted to illustrate that like doing this kind of machine learning process is something within the reach of most software engineers, I think. but we also have benefited from some expert advice from the Academy. Technically, again, I'm not going to get into too much detail here. We use TensorFlow as our framework. As I mentioned, we have an Inception v3 network underlying it. Most of our training has been done on hardware that's donated by NVIDIA. NVIDIA has a pretty long-standing relationship with the California Academy of Sciences, and they were generous enough to donate some hardware to us. So most of these models get trained in a computer at our office at Cal Academy. We've done a little bit of experimentation in cloud training, but found it to be very expensive. So we mostly work on these boxes in our office. So that's kind of how the computer vision system works at a very high level. But the next question that I hope most of us ask ourselves is it any good? Technically that's how it works, but does it actually provide decent answers and recommendations? And the first question that you might want to ask here is the underlying training data any good? Are the actual observations accurately identified? And to be perfectly honest, we don't have a great sense of that. The best kind of semi-formal study that we've done of this was this very small sample size study where we asked a bunch of experts to use a modified version of our software to identify a bunch of observations without seeing what the existing identifications were or who had voiced an opinion. So it's kind of a blind version of our identify interface. But again, it was a very small sample size. So take this with a giant grain of salt, but it's kind of what we have. So I figured I'd share it. This is the data that came out of that little study. And you can see there's variation in accuracy by taxon. So some taxa are better identified than others. And we've broken it out into things where the expert, matched the community identification exactly, or the expert chose something else, or the expert chose something that was coarser. Like community said, this is a black-backed gull, and the expert was like, it's genus Larus, and you can't really call it a species. And then imprecise means the expert did the opposite. So the community was like, it's genus Larus, and the expert said it's a black-backed gull. The main takeaway here is that the underlying data is in the 80% accurate range for most things. Also that there were a lot of birds. So if we'd done this again with more data, we might get slightly different results, but 80% kind of matches up with my anecdotal experience as well. So I suspect that that's still pretty good. So what about the model? This is an assessment done on only the computer vision model, or just one of them that we trained in 2019. I pasted over 2019 here because when I originally presented this slide, it was the latest model, but it's no longer the latest model. Anyway, the results in accuracy actually don't change very much from model to model. So it's about the same. This assessment was done with photos exported at the time of training only of the taxa that the model was trained on. So this is basically an assessment of how good the model is at recognizing the taxa that it knows about. So you can see that there is some pretty wide variation within taxonomic groupings and between, quite a bit really. But here we're talking about, on average, something in the sort of 75% range accuracy on the things that it should know, that it does know about. So that's interesting and pretty good. This slide is showing another form of assessment where we assessed both the vision model and the system as a whole, the system that includes nearby observations as well, using photos that were uploaded to iNaturalist after the training data was exported for the model. So these are both photos the model has never seen, but they are also potentially of taxa that the model does not know about. So how good is the model and the whole system at recognizing an arbitrary set, random sample of photos that it may or may not know about? And this model is this chart is a bit complicated, but the colored lines represents how frequently the right answer was in sort of like the top one for the red. So how frequently was the top result exactly the thing that the community called it as. The yellow line is sort of like how frequently was that community opinion in the top 2 and in the top 5 and top 10. I want to draw your attention to the left-hand side of dots here, the viz-only column. These are how well it performed with only the vision, so none of that nearby observation input. So you can see here in this, at least in this experiment, the top one result with just the vision testing on taxa that the model may or may not know about, it was only accurate 54% of the time. So it's like, you know, kind of a little bit better than a coin flip, but not super great. And then the other columns in here are different parameters we were testing for calculating the common ancestor taxon. So that's in this slide back here, that arachnida that we derive from the vision results. The columns are different ways of assessing that. It's kind of okay to ignore all of them. I just wanted to draw your attention to that gray rectangle one. So some important takeaways here are that when you do incorporate that nearby observational data, you get an accuracy boost of like 10 percentage points for almost all of these different top one, top two categories. So that helps out a lot. That whole process is enormously helpful for you, the end user, getting these answers. But again, we're talking about in the 64 to like 80% accuracy range. However, that top line, that mauve purple line at the top, that's the accuracy of the common ancestor. And that's really good. That's like 95% accurate. So in the app, when you see that line, we're pretty sure it's in arachnida. That means that we're pretty sure it's in arachnida. Like, that's a pretty reliable thing to choose. If you really don't know what you're looking at, that common ancestor is pretty good. If that's not there, and we decided not to return it, that probably means that we don't have a lot of confidence in most of the results. Yeah, okay. So I wanted to talk about some problems that computer vision generates it for us. And one of the ones that we wring our hands the most about is worrying that this robot that we made is racist. And so, like, what do I mean like that? What's the actual problem? The problem is that people are always observing humans on iNaturalist. As much as we say or try to indicate or imply that iNaturalist is for non-humans, specifically wild non-humans outside of your house, inevitably, I mean, there's wild things inside your house as well. Apologies to those of you who study in-house organisms, but most people who download the app are like I am, sitting on my couch in their home. And if they want to try it out by observing an organism, the nearest organism tends to be your child, your spouse, your parent, tends to be a human. So we do end up getting tons of human observations. And what we really don't want is to suggest to anyone that they are not human, that they are some other kind of organism. That is just a common form of racist insult and a common form of racism among people. And we certainly don't want this robot that we made to be like that, to make anyone feel like that. So there are a couple things that we do to try to get ahead of that. One thing I'll say anecdotally is that the system is extremely good at recognizing humans. So that human is almost always the top result. We don't tend to show, or I think we almost never show, a common ancestor for humans. The common ancestor, since humans, it's so good at recognizing humans, and humans always get a very high score, the common ancestor for humans is always the genus Homo, which we don't show because a lot of juvenile Anglophones use that as a homophobic epithet, and we want to prevent that from happening, so we don't show the common ancestor in those cases. We always show a menu of results in iNaturalist, so in that rare instance that human is not the top result, that's almost never happens as far as we can tell. Human is going to be in there, so at least they'll see that there's a range of options and that human is on the list. But we really don't want human not to be the top result. We've also locked down the taxon photos for humans and the ancestor of humans. So before we did this, we had these huge edit wars where, you know, the default photo for Homo sapiens was a picture of Charles Darwin, and some people were like, why does a white man get to represent all of humanity again? why does it have to be Darwin? Didn't change it to something else. And then someone changes it to Linnaeus, and then someone changes it back, and yada, yada, yada. We just ended that and made it impossible to edit those photos. And we editorially chose these mosaic images that we hope represent a diversity of humans. And that the further you go up the tree, we have humans in the mix with some non-humans. And we hope that the mosaic approach indicates that this is a taxon that contains many taxa, including humans. We definitely tried to choose photos that were on the cute side so that hopefully people would not take too much offense. But there's much more that we need to do on this front. We don't know a whole lot about racial bias in our human training data sets. And we don't know too much. We haven't done too much assessment using independent data sets as to whether or not the end results are biased towards one race or another, or if you get different results with different racial inputs. And it's a tough thing to do. It's tough to get data like that. It's certainly not something we'd want our community to crowdsource, have our community judging whether humans are of one race or another. That would be a disaster. So it's a challenge and something that we're continually working on. Another question that you might ask is it our training data biased, and in what ways? And the easy answer is absolutely. It's very biased. This accuracy chart that I showed earlier is showing you how you get different results for different taxa. That's indicating kind of like the different amounts of inputs, different amounts of taxa in different groups that gets included. So there's definitely a bias towards things that are easy to observe, like plants and birds, and a bias against things that are almost impossible to observe, like the mites that live inside the ears of birds. No one is photographing them. Very few people care about them, and they're very difficult to observe. So we don't get lots of those things. There's also a bias against things that are hard to identify. So the system is terrible at identifying spiders because people are terrible at identifying spiders. It's just very hard to identify spiders in photos. So yes, there are biases. It's good to be aware of them if you are planning on using iNaturalist computer vision systems. Occasionally we get this question, like, are you building something that's going to replace biologists? My job is identifying plants. Are you building a system that's just going to identify plants instead of me? And am I going to be out of a job? And I usually just point people towards our accuracy assessments and say, like, are you 54% accurate at identifying plants? If so, maybe the robot should take your job, but you're probably way better than this robot. iNaturalist's automated identifications are okay, but they are not good enough. They're not as good as an expert person, especially when it comes to harder stuff. So like if you're a grass expert, iNet's terrible at grass because generally, the community is not so great at identifying grass. Sometimes we get the critique of, by providing these suggestions that are somewhere between like 60 and 80% accurate, are you just creating circumstances in which people are going to blindly accept these robotic suggestions and create a bunch of crappy data? Because the robot is wrong a lot of the time. And, if you know INAT, you know that it just takes two people to make a quote unquote research grade observation. So what if they're both using a computer vision assisted tool and they're both accepting the same wrong suggestion that the tool suggests? So one way to get at this is this rather confusing chart that I made, sorry, but I'll try and walk you through this. So this chart is showing data from what I'm calling first identifications. So these are identifications that were added by the person who uploaded the observation. So it's like an own identification within 5 minutes of making the observation. So there's probably a little bit of slop there, but that's mostly people who are adding identifications without seeing any other input from the community. And we can divide those identifications between ones that were added with vision tools and one without. So like if you're using a vision tool, that means you saw a list of suggestions and you just chose one of them. And then without that means you manually type something in. And then these data are further divided into these improving and maverick categories. Thank you, Deb. Improving are identifications that were subsequently confirmed by the community. And then maverick are ones that were contradicted by the community. So an improving identification might be, I say it's a mammal, and then 5 people come in and say it's a dog. Mine was coarse, but it was accurate, according to the people who followed me. A maverick situation might be, I said it was a dog, and then 5 other people said it was a cat. That suggests that it's not a dog, that I was wrong. So those are mavericks. So what this is showing here in this top box in the dark rectangle is basically that the rates of mavericks compared to improving is pretty similar for vision and non-vision identifications. If you look at the absolute values in the bottom charts, you'll see that there's an absolute sort of more bad vision or maverick vision IDs, but like relative to the improving ones, it's pretty even, and the differences aren't really super significant. I'd also note that this is only including observations added on the web and in the Android app. Sorry, in the web and the iPhone app, because there's a little bug in the Android app that doesn't quite record this information correctly. And that there's far fewer Seek identifications because we just get fewer observations from Seek, and Seek launched a little bit after these other apps. With that, I just wanted to say thank you to all of the folks on the Inet team. Everyone contributes in some way to the thing as a whole, but also computer vision systems. I want to just highlight Abhas, who designed all of Seek, but especially that Seek Vision UI that I showed you. Scott's done a lot of work on exporting data and preparing the training data. Alex, as I mentioned, really spearheaded the whole thing. And continues to manage it. Patrick designed and built most of that observational data injection system that I talked about, all that common ancestor derivation, and then resorting the scores was Patrick. And then additional thanks to Grant for helping us out so much over the years, but also to everyone in the Inet community who has ever added an observation or identification. If that's you, then you have helped make Inet's automated suggestions better. And yeah, we are a joint product of California Academy of Sciences and National Geographic with additional funding from the Gordon and Betty Moore Foundation. Microsoft has donated a bit of time on some of their cloud GPU infrastructure for training. And then, as I mentioned, NVIDIA donated some hardware for us. So that's really great. With that, I'll take any questions y'all have.
Wow. Thank you, everybody. Thank you. Yay. Thanks. So there's a pile of questions. Kenichi, do you see the link to the Google Doc? I've also sent it to you on your phone, but it might be easier if you look in the chat.
Let me make sure that I'm not sharing.
There you go. That way you can look at the Google Doc, and I'll just give you 1 minute. I'll be happy to pick them if you like, but I thought I'd give you just a second to look at them because there's a pile there.
I'm just, if you could read them to me, that would be great, actually.
I can totally do that. So the first question comes from Dimitri Shigel, and he's asking about taking pictures from different angles. So for example, Inet is great. Everyone I know is a fan. And 2 thoughts. Any ideas to gently redirect attention from the most loved taxa and close-up areas to less popular ones? And another related to that is when you take a picture of an object of a taxa that you're not experienced taking a picture of, can Inet advise you on shots and angles? And the example would be like shooting a mushroom. And non-mycologists don't quite know that they need to see this cross-section of the stipe and gills.
Yeah, we've talked about that functionality so much over the years. You could definitely do some cool things with computer vision, some pretty simple things, and just say, like, if the computer vision model thinks that it's a mushroom, then we could just pop up a thing that says, like, hey, here's the 3 pictures that you want to get of this thing. We haven't done that. Why? I don't know. Just a lot of other things have come up. It's never sort of become a priority, but you could imagine a UI that does that a lot better job. We have worked, or there are some of the folks that we've collaborated with in computer vision over the years are researching technologies to indicate what parts of an image are most like a particular taxon. So that might provide additional help to an identifier. If you're sort of taking a picture of a flower, and the software could say, the thing about this flower that makes it unique is this spot over here, which might guide you to take a different photo and take a more diagnostic photo for human identifiers, which would be pretty cool. The first part of that question.
For example, could you point people to go to areas that haven't really been sampled?
Yeah, we've also talked about that a lot. Scott's put a bunch of thought into sort of like guiding people a bit more towards places where we know we have gaps in data. it's like many ideas that we have on iNaturalist, it gets rolled into bigger and bigger and bigger ideas that never get built because they become too big. I think that one got rolled into a lot of our like statistical modeling thoughts that have not quite hit the road yet. But yes, you could totally imagine a system that guides people. There are definitely some complexities with geography. You know, you might be indicating that someone should go somewhere where they really shouldn't be going. But yeah, I think that would be a cool feature.
Okay. A little bit different direction here. Vince Smith, he writes, I'm a journal editor for a popular data journal, and I'm starting to see manuscripts come in which describe INAT research grade data sets published on, sorry, let me go see where this goes, published on more systematic observations on the natural world rather than casual observations. And so the sub question to that is, does INAT want research-oriented field observations with photos? So,
do we want them added to INET?
oh, well, I think the first question
question
is, do you have any perspectives on this notion of the researcher submitting INAT research grade data sets and the use of INAT to collect more systematic observations on the natural world rather than casual observations?
Yeah, I guess it's a data quality question. Like, are we comfortable with people presenting collections or subsets of INAT data as useful for research? Yes, we are for the most part, especially when, you know, there are some curated collection of iNaturalist observations that are submitted in a paper. I've definitely heard from some colleagues that get, you know, negative reviewer comments when they incorporate iNaturalist data, and you know, some reviewers are like, well, that's just citizen science data, like it's probably not accurate. And it's sort of ridiculous because most researchers, if you're a responsible researcher, you have examined your own data and you have some sense about how accurate it is. So when it's presented as a part of research, I hope any researcher has taken the time to do a little bit of QA and QC. So yeah, I'm very comfortable with people doing that as long as they have some knowledge about what they're using. In terms of people uploading what they think is better quality data to iNaturalist, if it's stuff that you generated yourself, great. If it's stuff that's just a collection that you have on hand that wasn't something you personally experienced, then not so great. Again, our mission is trying to facilitate those personal experiences. So if you just have a database of stuff that you want to get out there, talk to your local GBIF representative, and they will help get it integrated into the local GBIF node.
All right.
And that's probably not the best place for that.
Yeah. Okay. Next, I love the gamification aspects of Seek, and I miss them since I've moved to iNaturalist. Are there plans to bring those to iNaturalist?
No.
Short answer.
Yeah. The longer answer is that I'm pretty anti-game. I like the unstructured nature of natural history. Mm-hmm. That's what I'm into. It's part of why I built Inet. And I don't like the idea of artificial incentives. You know, mm-hmm. I don't like a computer telling me why I should value nature. I value it. My reasons are my own, and I want iNaturalist to be a tool that helps me and not one that tells me what to think. That is a very narrow view of what a game is. And people who are pro-game might be insulted by that, and I apologize for that. The reason we built Seek is just an acknowledgement that there are different ways of thinking about nature and different ways about different ways of motivating people and incentivizing people to get out there and pay attention to things. So they're meant to provide different experiences for different people, and we're going to keep them separate.
Okay, thank you. Certainly we know that motivation is individual to the youth, that's for sure. Steve Baskoff asks a question. He says, it's similar to question 1. Have you considered suggesting to users that they take additional photos, different views of the organism in that case, and where it's likely that the taxon is hard to identify, or taxa where you don't have good coverage? These could be directed to experts who would then give a reliable ID and improve your training data set.
So indicate or motivate people to observe things that are rare. Is that the notion?
I think so, but like you, I was trying to read these as they came in and listen to your talk. So I'm parsing all of this along with you. I do think Steve is somebody who goes out and takes pictures repeatedly. He'll go back to the same tree year after year, for example. So taking different views is important, at different times of the year is important. But he's also pointing out here where the taxon is hard to identify or for where you don't have good coverage. So again, that gets back to that sense of, is there a way you could imagine suggesting to users that they take additional views or, and then could be directed to experts. I think he's got a second part of the question there, which is could then you direct those to experts who could help ID them?
So the in the moment suggestions, if it's something that's rare and hard to identify, that probably means that our automated systems are also bad at identifying it. So like we can't automatically know that you're looking at the rarest species of mosquito or something like that, right? Mm-hmm. What we can know is where the gaps are in our existing data and guide people towards observing those. That could be spatially, that could be temporally, and that could be taxonomically. So we could say, you know, we just don't have enough mosquito observations in Alaska. Everybody go to Alaska in June and find all the mosquitoes. And you know, we could guide people in that way, and we've certainly thought about it. We just have not gotten around to doing it.
Okay, I look forward to that. I'm off for that adventure. Oh, next up is Siobhan Leachman, and she writes, I add images from Wiki Commons to iNaturalist species pages. These images are sourced from museums or research institutions. These particular images are expertly identified to the species level. Do you use these images in the training model, or is it just observation photos added to iNaturalist by citizen scientists?
Just observations.
Okay. We could ask why or why not, but that would go on for a bit. Maybe we could talk about that offline, and we could add it in the document, perhaps. Kat Chapman asks, she might have missed this, but she wasn't sure. What are the long-term plans for iNaturalist data?
I'm not sure there is a plan. They will continue to grow.
Yes, it's growing exponentially, I mean, is it not? Is it not sort of asymptotic, the images?
Yes, it is still growing exponentially. I think, yeah, a lot of people think that we sort of have an agenda. I think, you know, a scientific agenda, maybe because eBird does, like eBird's, part of eBird's mission is to do science on the data that they're collecting. Mm-hmm. We don't really have that mission. We just view ourselves as stewards of the data and of the infrastructure. And we hope that it is useful and accurate. We care about those things, but we don't necessarily have research agendas of our own to like try to study something based on the data.
Thanks. This next question also comes from Vince Smith. He writes again, sorry, but Vince, we're not sorry. And you may have partially answered this in your talk, but I'm not sure, so let's see. Do you have any perspectives on the extent to which images of specimens in natural science collections can be used to help the training algorithms? Or are you restricted to images taken in the natural world? We kind of just said, I know that there have been a few publications on this, but perhaps for the more unusual or obscure taxa that are rarer in your training set, these collection images-based images might be very helpful.
We don't, we don't have a sense for whether or not they would help or harm our vision model's performance on those rare taxa. They'd probably help, frankly. Mostly that's just because like there are many things that we'd like to experiment with, and that's one of them. Many people have approached us and said, you know, we have a very large database of burying beetle images that will probably help out your model. And our response is usually, we're pretty slammed in just managing our own training process with what we have. But I would love to see an experiment, just see like, well, how would that affect the model? Would it actually make it better at recognizing in situ photos of those species? Is the model going to key in on the right visual attributes, or is it going to key on like the presence of a label? Unknown. So yeah, it'd be great to see some research on that topic.
Okay, we have time for maybe 2 or 3 more. Squeeze them in quick, okay? Seek is pretty good at being tentative with its suggestions. Have you explored user interface changes on iNaturalist itself so that people are less likely to slam that top suggested species level ID and go with a pretty sure higher taxon instead?
We could change the UI a little bit. We could change the parameters for choosing that common ancestor or not. But I think the easiest, the best thing we could probably do is just ditch the not nearby stuff. That would be the biggest interface change that I would want to see. And I'm hoping that we're going to start doing that in the Android app sometime soon. But beyond that, not too much.
Okay. Toivo Yulinampa asks, do you use data augmentation for underrepresented species? Do you see TensorFlow as the best option, or have you considered PyTorch?
I think we have considered PyTorch, and again, this is reaching the limit of my technical knowledge. If data augmentation means something more than augmenting the training data with other stuff, then no. But if it means sort of making synthetic training data, then also no. But I can try and relay that to Alex. He might have a better answer for that.
Marvelous, thanks. The next one on the list here is, do you have any concerns about Inet's computer vision decreasing the perceived biodiversity by creating a relatively closed feedback loop? It goes on to, or she goes on to explain, I do not know. You mentioned CV, geographic bias, for when the suggestion is likely not found in the location of the observation. But what about species that are found in the area, but their presence is masked by the CV not knowing they exist, because new observations keep getting the same identification suggestions? I think the subtext there is, it says, are the ignorant leading the ignorant?
Right. There's a bit of, I mean, I have a reasonable amount of faith that people are reviewing things and adding contradicting identifications to combat that, especially within groups that do have similar kind of lookalikes. You know, if there's a rare version of something that's people are paying attention to. But that is a concern for sure. I think people are definitely paying less attention to the common stuff and more focusing on the rare stuff. Mm-hmm. Yeah, that's an interesting area for inquiry. Not sure how we would approach it, but it's an interesting question.
Okay, I think, and my moderators will help me if I'm wrong. We have time. I maybe can ask one more quick one, but we're kind of done here. But we do have another, let's say, 10 or questions or so. So maybe we can give those to you, and people have given their names, so we would be able to contact them, and we put the answers in this document, and then they can come back here and look at them. Does that sound good?
Sounds great.
Can we do that? Okay, so we can finish with Josh Humphrey's question. Do you have any data about how specific the location data has to be to positively influence the classification? For example, is country/continent enough, or does the accuracy of the location have to be better than that?
I'm pretty sure the only thing that we're using in that nearby observation conditioning is the coordinates. So I'm not sure if we're even paying attention to the precision, assuming we even get it. As I mentioned, that nearby observation search is not at like a place level. So it's not like the app is saying, this person was in Russia. It's saying, this person was at this set of coordinates, search near these coordinates. So that's not quite how we do the search. It might get different results. My suspicion is that it's better to do something more neutral and geographic than based on places, since places are weirdly shaped. And even where I live in California, you might just end up getting a lot of weird Southern California stuff if you're observing something in Northern California. For sure.
Well, I want to thank you on behalf of TDWG, on behalf of all of our participants here at the conference. That was an amazing walk through the world of iNaturalist and the behind the scenes peek. And the interest here is clear when you see in this document, right, the number of questions that are waiting for an answer from you. So we appreciate that, and we look forward to seeing those. But now we have to move on. But thank you again from all of us. Yay.
Cool. Thank you all.
We appreciate it, and we look forward to the answers. We're not sure when you have time to get to that, but we'll be peeking. Thanks, Kenichi. Thanks, everyone. We'll have a 5-minute break now, and then we will come back in 5 minutes to start the business meeting. Thank you. Woohoo! Hello.
Hey, that was fantastic.
I just put a line in the document to try to note
Yep.
the break.
Yep,
Okay.
I saw it. That was great. So hopefully Kenichi has time. He can go in, and I see, there's just a ton here. So
Should we stop recording and stop streaming?
did we?
We should stop streaming for sure. I don't
Oh.
know if we're going to record straight through. We probably shouldn't.
I'll
Should
break
stop.
the recording.
Yeah. And we don't need to stream the business meeting. Bye, all.
Please
You
no.
are watching on YouTube. Ciao.
William will need to stop that.